there are questions about anything we've been doing so far.
So just some terminology. You use the terms like authentication and verification. Was it the other one, or similar?
I mean, there's, yeah. Well, there's there's authentication, which is the private key version. Basically, Alice wants to authenticate a message to Bob so that Bob knows it came from her. There's a notion called digital signatures I mentioned. I don't know if that's what you're thinking of.
No, I think authentication is the one that I was.
Yeah.
I was just wondering.
I mean, verification. The word verification gets used a lot too, but.
I mean, I vaguely understand what it means, but you know.
Okay. Yeah. So I mean, so in cryptography, people like to come up with really careful, rigorous definitions because sometimes you can get tripped up if something doesn't mean exactly what you think it means. For classical authentication, so usually these security definitions have two parts, which are the soundness and completeness. So completeness just means that if there's no adversary, it's doing what you think it is. So completeness means, authentication protocol, here I should probably write this. So authentication protocol is, so it's going to be some map from messages to a message with some signature tag, some extra thing that you append on, and then there should be a verification function that that takes these inputs and outputs yes, no, basically. And so the completeness property, this is authentication, or sometimes called message authentication. So the completeness property just says that if there's no adversary, that Bob will correctly. So this, yeah, okay. So these procedures are both based on some key K. And the completeness property is straightforward. It says that if you verify, yeah. So this thing doesn't have to be. Right, it's just some other sigma that might or might not be right. So the function works on both. And if you apply it to the correct signature, then you get yes. So this means that Bob will accept. And you might modify this to say with high probability or something like that if it's a randomized algorithm. But this is the basic thing. And then the soundness. So I'm not sure I can replicate exactly the correct definition of soundness in this case, but it's going to be something like so you're going to have an attack by Eve. Is this what I want? So there's various types of security definitions as well. This is for one-time authentication. Eve is going to have access maybe to one signed message. And the idea is she should not be able to create a different signed message. So you're going to have some attack by Eve. That takes as input one signed message and is going to output somehow some other thing where m prime is not equal to m. And the idea should be that with high probability over k, that vk of m prime sigma here So I guess we'll call it the image here of M yeah, okay, let's just leave it like that. So this is kind of, I can't guarantee that this is exactly the correct definition, but it's kind of roughly correct. And like I said, if in cryptography, if you get the definition wrong, frequently that can create a security hole that somebody can take advantage of, so you have to be careful about these things. Okay, and then you can kind of upgrade this to say, well, what if she has many messages and stuff like that. Other questions? OK, so what I want to talk about today is what goes by the name of quantum information theory. So it's the quantum analog of a classical field called information theory, which is basically the study of information and trying to understand how you quantify information and what you can do to manipulate information into other forms. It's different from computation. We're not so interested in the number of computational steps, although the practical aspects of it definitely have to take that into account. It's more a question of kind of how much information you have and what that means. OK, so the basic, probably the most simple, but also one of the central quantities that will come up when talking about quantum information theory is the von Neumann entropy. Which is, so if you have a density matrix rho, then the von Neumann entropy is minus trace rho log rho, base 2. Up to having the base 2 and maybe some factors of kT, this is the thermodynamic entropy. Basically, so up to constant factors, it's the thermodynamic entropy. There's a whole story about how that's connected, which I don't want to get into. What I do want to get into is how it's connected to a classical, very analogous classical quantity, which Shannon also called the entropy. And so the Shannon entropy is usually called H. And it's the entropy of a probability distribution. So this is going to be the probability distribution. And that's minus sum over, so there's different outcomes I that have probability pi. And the Shannon entropy is minus sum over I pi log pi. And in this case, yeah, so the base 2 here and in the von Neumann entropy is so that we can measure entropy in bits, which is, of course, a standard way of doing anything relating to computers. You can see that this quantity is just a special case of this one, right? When rho is diagonal, then its diagonal entries, its trace is 1, so diagonal entries form a probability distribution. They also have to be positive because it's a positive semi-definite matrix. So they form probability distribution. And the trace means just summing over those diagonal entries. So this is exactly the same formula. OK? So the Shannon entropy, and by analogy, the von Neumann entropy, quantifies how much information is in a system, is in a probability distribution, which you can think of intuitively as being, suppose you draw one sample from this probability distribution. How much information do you gain about it? Right? So if you have a distribution that's kind of very highly peaked, so you're flipping a very biased coin, and it's almost always heads. You flip it, and it turns out to be heads. You're not surprised, right? You're not really gaining information about it. This is the assumption that kind of what the probability distribution is, but you don't necessarily know what's going to happen with it. So that's the sense in which you're gaining information. Okay. On the other hand, if it's a fair coin, if it's equally likely to be heads or tails, then before you flip it, you have no idea what's going to happen. And so when you do flip it, you really are gaining a full bit of information, right? And that's what happens here when there's two outcomes and both of them are equal to a half, right? You get a half log of a, so log of a half is -1, so that cancels this minus here. We need the minuses because these are all negative. And so you get a half plus a half. So the entropy then is equal to 1 bit. OK? Yeah, so I'm not going to – I'll have a lot more logs probably in this lecture, but I'm not going to write the base 2s anymore. So you should assume that they're base 2 when I don't write anything. OK, so we can certainly think of the von Neumann entropy as if rho is a mixed state, it can be a mixture of pure states. We can even think about it always in the diagonal basis, and then it's really just exactly the Shannon entropy. But remember, rho could also be part of an entangled state. And so often what we do in the theory of quantum information is talk about the entropy of subsystems of some bigger system. And so when I do that, I often use a shorthand. So instead of talking about, so rho A here was the trace. You have rho of some bigger system. We trace over everything but A, and we get rho A there. But I might just write this as S of A. OK? And similarly, if you have multiple subsystems and you trace over everything but A and B, you might have S of rho AB, which I could write as S of A comma B. OK? So the von Neumann entropy has a bunch of properties that are useful. So let's list some of them. They're going to have enough space here, but OK, let's try. So if the dimension of the Hilbert space is big D, then the entropy is at most log of big D. And we get equality when we have the maximally mixed state. OK? So it makes sense, again, that the maximally mixed state would be the state that has highest entropy, right? Because that's the one where you don't know at all ahead of time what's going to happen. And if you calculate it, you'll immediately see that it has log D, right? Because you get each one is log D, and you get 1 over D log D added up over the D entries. OK? So that's the maximum value. The minimum value, because all of these things are negative, that we always get something non-negative. And so S of rho is greater than or equal to 0. And S of rho is equal to 0 only if rho is a pure state. Again, thinking classically, which you can do because you can diagonalize rho, this is not at all surprising and easy to derive, because you just say, well, that's the case where it's a pure state means that there's just one possible thing it could be, and it's always that. And so I'm not getting any information by seeing that it is that. And again, you can verify that very easily because, well, 0 log 0, you have to look at the limit where that's 0, because the log 0 is slower than the 0 before. And 1 log 1 is 0 as well. OK? OK, so the next thing, this is the triangle inequality, also known in this case as the Iraqi-Lieb inequality. And that says that if you have a joint system, AB, the entropy of that is at most the absolute value of S of A minus S of B. Okay? So, yeah, okay, let me not comment on that until I do the next one. So subadditivity. So this property says that S of AB is less than or equal to S of A plus S of B. So what this is saying is that if you have two systems, A and B, then the total entropy of the system is at most the entropy of this one plus this one, right? But it is subadditive, and so the time when you get equal is when A and B are uncorrelated. When they're correlated or entangled, then the entropy of the whole thing can be smaller, right? And it can, in fact, be as small as 0 if there's a joint pure state, and these two are half of this joint pure state. Particularly if it's entangled, then they're both non-zero. Both halves are non-zero, whereas the entropy of the whole thing is 0. Okay? So that's telling you that the entropy of this whole thing can be smaller than the entropy of these pieces, which doesn't happen classically. Classically, S of AB has to be greater than or equal to S of A. And so this thing is different in the quantum case than the classical case. But this is a limit to how much smaller it can be, right? So, so equal if uncorrelated. And so you can think of the system B as so if S of AB is equal to S of A, then that's kind of saying that B is completely correlated to A, classically anyway. That's saying that everything you know about B comes from stuff. Everything if you find out what happens to A, you won't be at all surprised by anything that happens in B, right? That's just derived directly. Okay. That would be saying the conditional information is 0, but I'm not going to get into that. In the quantum case, it could be that B is soaking up some of the entropy of A through entanglement, right? Because if you have an entangled state between the two, it's a pure state, and it could be a pure state, and that would be 0 entropy. And this is saying, well, the most amount of entropy that B can soak up that way is equal to the entropy of B. Okay? So that's what this is saying. And this is limiting how much lower than the entropy of the joint system can be if A and B have kind of different entropies. Okay? And then there's another property that you commonly see. So these ones are relatively easy to prove. This one is not easy to prove. It's called strong subadditivity. I should say it's not easy to prove quantumly. Classically, this is still true, and it's much easier to prove. Pretty straightforward. So this is saying if you have 3 systems, A, B, C, then the entropy of the whole thing altogether is S of AB plus S of BC minus S of B. And obviously, this is not symmetric, so you could, but there's no preference for A, B, and C, so you could substitute them in any combination. Okay. And just as an analogy to think of this, you can think of kind of a Venn diagram. And here's A, here's B, and here's C. And so S of ABC is the whole thing, right? And AB is the thing on the left circle. BC is the right circle. But then you see if we've kind of added both AB and BC, we've double counted B in the intersection. And so we subtract it off. Now that's just an analogy. You shouldn't generalize this. It doesn't. I don't think it holds to more general entropy inequalities. But it does kind of help you remember what this formula is. OK. And then I just want to write down one more property, which is not an independent property. It comes from 2 and 3. But it's so useful, and it comes up so often that I want to write it down specifically, which is that if rho AB is pure, then S of A equals S of B. So you can immediately derive this from 2 and 3, because if rho AB is pure, then SAB is 0. And that means that this is 0 here, greater than or equal to this difference, which absolute value, this has to be greater than or equal to 0. So they're actually equal. OK? OK, so any questions about entropy? Yeah.
For that last point, do A and B have to be like equal size regions?
They don't have to be equal size regions. It could be that one of them is much bigger than the other, but maybe the small one has maximal entropy and the big one does not.
Oh, yeah.
Yeah.
I guess, I mean, this is probably a little bit outside of the course, but do some of these properties generalize for infinite dimensional systems? Or?
Well, I mean, all of these except the first one apply to any system, I think. Yeah, I mean, some of these equations might not be well defined when the entropy is infinite, but other than that, it doesn't depend. I'm pretty sure about that. Any other questions? OK. So OK, let's see. I have to figure out how to do the blackboards now. OK, so so now let me move on to kind of information theoretic protocols. And in particular, I want to talk about data compression. And so a little spoiler alert, the entropy is going to show up. And you'll see that data compression you can use as one of the motivations for talking about entropy. OK, so let's first talk about classical data compression. So data compression, the basic idea is, again, we have Alice and Bob. And Alice wants to send information to Bob. And now there's no eavesdropper. There's no noise. Everything is perfect. But the communications channel between Alice and Bob costs something. There's a limited number of times that Alice and Bob can use it. And so Alice wants to send the most possible information she can to Bob, or send the most messages to Bob, with the minimum amount of communication. OK, so how can they do that? And and again, this is something I'm writing it as a communications problem, Alice sending to Bob, but you can also use it for storage, right? If Alice wants to store something on her computer and she doesn't want to take up the maximum amount of memory, she wants to minimize the amount of memory it uses, compression is again the answer. And compression is very widely used in classical systems, right? Basically every file format you would see nowadays, except for the really extreme ones, kind of primitive bitmaps are not compressed, but everything else is compressed. JPEG, GIF, MPEG, PDF, all compressed. Okay? And the reason is because you can get pretty substantial savings in terms of the amount of communication and memory you use. And so that's another important factor if you want to have high-speed communications. OK, so how does it work? Well, what's the basic idea anyway? So let's look at an example. Very simple example. So A has 4 possible messages. And the key is that, sorry, let's Alice, so I'm going to use A for the messages. Alice has 4 possible messages. And these messages will occur with differing probabilities. And that's the thing that's going to make this work. So we have A with probability 1/2, B with probability 1/4, C and D each have probability 1/8. OK, so since there's 4 possible messages, the simplest way, the most naive way, would be for Alice to send 2 bits to Bob, right? That could specify which of these 4 messages she has. OK, so that's the baseline. OK, so here's a compression scheme that's going to do better. And the idea is, well, the message A is quite common, right? It happens half the time. So we should use a short message to encode A. And then the other ones we can use longer messages for. So in particular, let's encode A as a 0 and B as a 2-bit string, 1, 0. And then C and D, they're kind of rare. So we'll encode them as 3-bit strings, 1, 1, 0, and 1, 1, 1. OK? And so let's calculate the average number of bits that Alice needs to use to send a message to Bob. Obviously, if she just sends 1 message, well, sometimes it's going to be short, but sometimes it's going to be longer than 2 bits. But let's suppose she's doing this many times, sending many messages drawn from the same distribution. And each time she looks at the message, and then she encodes it this way and sends it to Bob. Bob decodes it. Alice gets another message, and she encodes it, and so on. So on average, how many bits will she use? Well, so half the time, she's using 1 bit. And a quarter of the time, she gets B, she's using 2 bits. And when she gets C and D, each with an eighth of the time, she uses 3 bits. OK? So this is a half, and these are 3/8. So adding that up, we get 1 3/4. OK? And so that's less than 2. We saved a quarter of a bit on average per message. Right? So if she's doing this 1,000 times, saving a quarter bit per message, that's about 250 bits that she saved. OK? So that's the idea of compression. And obviously, this is a very simple case where the numbers are chosen so that you can kind of exactly write this down and calculate everything very easily, and make everything work. And there's another nice property of this particular scheme, which is not necessarily going to be exactly followed by all compression schemes, but is going to be almost followed, which is, let's look at the first bit of the message that Alice sends. OK? Well, half the time it's going to be 0. And then a quarter plus an eighth plus an eighth, half the time it's going to be a 1. OK? So the first bit that Alice sends is equally likely to be 0 or 1, which wouldn't be true if you were using this naive encoding, right? Because if you did like 0, 0, 0, 1, 1, 0, 1, 1, then she'd be sending 0 on the first bit 3/4 of the time. OK, what about the second bit? Well, certainly if the first bit was 1, then the probability of the second bit being 0, well, conditioned on the first bit being 1, it's a half of getting B. So it's a half of 0, and then a half of getting 1. But also, if the first bit was 0, then the second bit is starting a new message. And so it's also 50% likely to be 0. So the first bit and the second bit are both equally likely to be 0, independently of each other. And if you work it out, it's the same for the third bit, right? If we got 1, 1 for the first 2 bits, this one is equally likely to be 0 and 1. If we had 1, 0, then this one is equally likely to be 0 and 1 because it's starting a new message. And this one here is the second bit of a new message if we started with 0. And so that's equally like, or it could be that if we got 0, 0, then it's the first bit of a third message. So every bit in this scheme, even when we use it many, many times, is equally likely to be 0 or 1. So if we do this many, many times, the bit string that's actually getting sent over the channel is a completely random string. OK? And that's the real insight and the real goal of compression, right? Because that means that we're using all of the possible strings, bit strings, equally. So we're making kind of optimal use of the communications that we have available. And so that can motivate this more general compression scheme. So this is actually not just a single scheme. It's kind of a class of schemes called block coding. And so the idea is, so let's imagine that we have what's called an IID source. So independent identically distributed source. And by source, I mean source of messages. So something is generating these messages. Alice is getting them, and then she wants to send them on to Bob. So let's say it has probability distribution PI. And so if we have n messages, so the way we want to do compression is we're going to look at kind of the most frequently occurring messages. We're going to look at a typical set of messages, which collectively appears with probability very close to 1. And we're going to line those messages up, and we're just going to say, OK, we have so many bits that we're willing to send in this compressed scheme. And the first of these typical messages is going to get the compressed version all zeros. The second one is going to be 00001. The third one is 00010, and so on. OK? And the order doesn't really matter. That's going to affect the computational complexity, but it's not going to affect the efficiency of this scheme as a compression scheme. So the idea is we're just going to write down all the typical messages and then have a compressed version of those. And if we have a message that's not typical, that happens with very low probability. And so our scheme will just not know what to do. We can put in something random. And so that means this is not going to be a perfect compression scheme. It's just going to have high fidelity to the right state. Because if we happen to get very unlucky and get one of these atypical messages, then Bob will not reconstruct it properly. But most of the time, and in the limit as n gets large, that means exponentially close to probability exponentially close to 1, Bob will be getting the right message. Yeah.
So I mean, this whole process assumes that both Alice and Bob have the same set of A, B, C, D.
Yeah. So this, as I've described it so far, they both know what the distribution of messages is. They don't really need to know what the distribution of messages is. That's used to design the compression system. If you have a system that's designed for one distribution of messages and you actually have a slightly different distribution, it'll work pretty well. But you won't necessarily have kind of the optimal. Well, there's two possibilities. So one is some of the atypical messages will be more likely than you thought. And that's bad because that means that you'll fail more often than you thought. But if it's close, then that shouldn't be too bad. It depends on the details of the scheme. But the other thing, of course, that can happen is you just won't be compressing as efficiently as you could have. Now, there are also compression schemes that don't depend on this. If it's really an IID source and you're getting n messages, then you can use the first some number of messages to kind of figure out what the distribution is, and then have a universal compression scheme that compresses based on that. That's much more complicated in practice, but the basic idea is like that. So real-life compression schemes usually take advantage of knowing kind of what sort of thing it is. If you're compressing a picture, you know what kind of distributions. And that's not an IID source anymore, right? Because you have a lot of correlations in the picture, and so you try to take advantage of that as well. But yeah, it's definitely helpful to know what kind of thing you're compressing and what the distribution is, but it's not completely necessary. OK, so how are we going to do this? So if we have n messages, what's the probability of getting ni I messages? So of getting a particular sequence. Well, that's the product over I, pi to the ni, right? Because the first message will have some value, and that occurred with probability. So say the first one has I1, and so that will give us a factor of pi1. The second one is pi2 and pi3 and pi4. And whenever this particular pi appears, we get another factor of that pi. And so this is the product for this particular sequence. OK? Now, for any sequence with ni, well, we should throw in some combinatorial factor, right? Because there's many different ways of distributing these things. We get, so there's n factorial altogether, possible orderings. And we have the product over I of ni factorial on the bottom. Right? This is the generalization of n choose k to having multiple different things. Okay? So this is the number of different orderings of messages that give you ni of message type I. Okay? And so then we multiply this by the product I pi to the ni. And this thing here, you know from studying classical probability theory, gets very highly peaked around the case where ni is roughly pi times n. Right? That's just intuition. That's kind of the frequentist version of what probability means. That if you take many samples from a distribution, the probability pi means that you'll get about pi times n of that outcome. OK? So this is telling us then what the typical sequences look like. The typical set is all bit strings, all message strings, with about pi times n of message I. Okay, it could be a little bit more, a little bit less. There's going to be some variance. But that's not going to affect the counting very much. OK? Is everyone OK so far? So now we have our typical set. And so now we want to do our block compression scheme, which is to say, for each element of the typical set, we want to come up with a distinct bit string. And so how many different bit strings do we need? How many elements are there in this typical set? Well, we can calculate that using Stirling's formula. I'm going to take the log of that. So the number of things in the typical set is this combinatorial factor, right? Where ni is equal to pi times n. So the number of things is n factorial over product over I, pi n factorial. And to figure out, and the number of bit strings we're going to need is 2 to some power. The power being the number of bits that we need. So let's take the log of this. And again, this is the log base 2. And Stirling's formula tells us that log of n factorial is about n log n. And so then we have minus sum over I of pin log pin. OK? And of course, log pin we can write as log pi plus log n. And this log n in here doesn't depend on I. So we can write this as n log n minus sum over I pi n log n. And then we have the term where both things do depend on I minus pin log pi. OK? But of course, this is a probability distribution. So the sum of over I of pi is 1. And that means that this term here cancels this term here. OK? So we're left with this. And this, you should recognize up there as n times the Shannon entropy. So these are not products. These are equal. OK? So what this is telling us is that the number of bits we need in order to have a unique bit string for everything in the typical set is just n times the Shannon entropy of the distribution. OK? So this is a concrete operational sense in which the Shannon entropy is a measure of how much information there is in the distribution. It's saying actually, literally, in the conventional sense, how much information you need to send this distribution, or samples from this distribution. Okay. Yeah?
And if the source is not IID, will that be less?
Yes. Yes. I mean, in that case, you shouldn't really be representing it as individual probability distributions for the source. It could be. I mean, it could be. Yeah. I mean, I guess you could generalize immediately to the case where it's independent but not identically distributed. But once there start to be correlations, yeah, it could be a lot less. OK. And the flip side of this is that you can't. Yeah. So let me write down the theorem. So basically, what I've shown you so far is a sketch of the proof of Shannon's source coding theorem. Which is one of the central theorems of classical information theory. And the thing that's missing is mostly the epsilons and deltas of kind of getting everything precise. And what it says is, suppose we have an IID source with entropy H. And we want to encode n messages with probability of failure going to 0 as n goes to infinity. Then we need at least n times h with maybe some small correction. This is little o of n, so it's strictly smaller than n asymptotically. Bits, and there exist, maybe I should say minus here, and there exist compression schemes using only that many bits. Okay, so so this block coding scheme is an example of a scheme that achieves this bound, right? By the argument I gave, you look at the typical set, you count how many things are there, and you see that you can do it with n times h. Now, but almost the same argument, I mean, a related argument anyway, shows you that you need at least that many, right? Because you have to encode pretty much everything in the typical set. If you don't do that, then there will be some things that occur with high probability that you're not correctly compressing. And so your failure rate will be too high. Now, you don't have to, the typical set is not unique. You can adjust it in various ways. You don't have to pick every single message in the typical set. You could exclude a small number of messages, and it wouldn't change the asymptotics. But it also won't save you much if you do that. OK? So that's the basic idea behind this coding theorem. OK? So there are questions on that. That was just classical compression. OK. So then let me very quickly do quantum compression. And I can do that because quantum compression is very similar, very closely related. Quantum compression is also called Schumacher compression. This was invented, discovered, whatever, by Ben Schumacher. And so in this case, instead of getting a probability distribution of classical messages, we can imagine that we have a probability distribution of quantum pure states. So with probability pi, we get the state psi I. Okay? And we know that we can write this as a density matrix. It's a mixed state, right? So we write it as a density matrix, sum over I, pi psi I. But it turns out, well, OK, so of course, this density matrix doesn't have a unique decomposition this way. Right? There could be many different decompositions. And there's no, if you're just looking at the density matrix, the system, there's no way of telling between these different decompositions, right? They're indistinguishable. And in fact, you can achieve them all by purifying the system and doing different measurements on the other system. And that's what we want to do here. So there's going to be a reference system and Alice's system. And the goal of quantum compression is to do some encoding here so that the number of messages, the number of qubits she needs to send to Bob is smaller. And then Bob will do some decoding. And what we'd like is that, so this is the input state rho, tensor n. And this is, let's call this output state sigma tensor n. And we want sigma tensor n. Sorry, I should, let me fix this. So this is a purification. So this is not rho anymore. This is some pure state psi. And the output, in principle, could be a mixed state. but it's a bipartite mixed state. So it's here we have B. So this is the state of BR. And so we want that to have high fidelity to the input state on A and R. Okay? So this is called the entanglement fidelity, and this is so this is certainly something that's desirable, right? If what Alice is getting is actually not some probability distribution of pure states, but it's actually part of some entangled state, we want then Bob to be able to recreate the entanglement with that reference system. But actually, it's kind of the same thing, right? Because it could be that the person holding this reference system really just, with some probability, they chose the state psi I. And they just didn't bother to figure out which one it was. So that means that they're doing some measurement here. When they do want to figure out which one it was, it could be here. They do some measurement here. And they say, oh, it was actually the state I, state psi I. And they could do that measurement here. They could do it here. Or they could do it here. And since this does not involve Alice and Bob, they could get the same result, right? And so at the end of the day here, you can say that Bob is producing the state psi I if the reference system measured it early on. Or you can say they're preserving the entanglement if they're measuring it late. And they're exactly the same thing. OK? So this is the quantum way of saying that we want the output message to be the same as the message that Alice was given. OK? Does that make sense? OK, so how do we achieve this? So it's so if Alice works in the basis where rho is diagonal, then so again, this is a case where Alice knows rho. She doesn't know necessarily what the pure states are, and certainly not what any particular pure state is. She knows rho, and Bob knows rho, so they can work in a basis where rho is diagonal. And then they can think of this distribution as just a distribution of over orthogonal states, a classical probability distribution over orthogonal states. And so working in that basis, they can just treat this as a classical compression scheme, meaning that now everything should be done coherently to preserve entanglement with the outside. But Bob can do this. Alice can do the same classical compression scheme, just do it with reversible quantum gates. Make sure she erases all scratch bits and stuff like that. And then send the resulting qubits to Bob. And Bob decompresses, again using the classical protocol in this basis. And so the upshot is that you need then S of rho n messages, or qubits, to send n messages of this form. OK? So as in the classical case, there are universal compression schemes that do some gentle measurements on rho, the first some number of uses, in order to figure out what rho is without really disturbing rho. And you can do that because while identifying rho from one copy, there's inevitably going to be some failure and some disturbance of rho. When you have many, many copies, there's kind of a deterministic answer, because all of the rho tensor n is very distinguishable from rho prime tensor n, when rho is not equal to rho prime. Even though rho and rho prime might be very close, once you get many, many copies, they become more and more distinguishable. Okay? So if you have enough copies, then they're very distinguishable. Alice can kind of learn rho to a very high precision and then figure out what the right compression scheme is to use from that. Again, that's more complicated, but it still asymptotically gives you the same rate. Because you don't need infinitely many copies to do this. Okay? So that's all I wanted to say about compression. Are there any questions about that? OK, well, I'm almost out of time, but I'm also almost out of lectures. So let me just tell you Shannon's other major theorem, kind of the other pillar of classical information theory. And then we'll talk a bit more about that and the quantum version of it tomorrow. So, so this one is called the source coding theorem, and this one is called the channel coding theorem. And the source coding theorem was for compression. It's for the case where the channel is perfect, Alice and Bob's machines are perfect. The channel coding theorem is for error correction. It's for the case where the channel is introducing noise. And of course, we already talked about that scenario in the finite case. So the channel coding theorem is talking about the case when n is going to infinity, when we're sending many, many bits over this noisy channel. And it says that suppose we want to have a protocol and it's to send n bits through a noisy channel with IID noise. So what that means in this case is that every time we use the channel, each bit that gets sent through the channel or higher dimensional register experiences some noise, but it's the same noise for every bit, and it's independent. And again, we want asymptotically the logical error rate approaching 0 as n goes to infinity. Then, again, like the source coding theorem, the channel coding theorem gives you upper and lower bounds on how many bits you need to do that. So the scheme uses at least n over c minus little o of n bits where c is a property of the channel called the channel capacity. There also exist schemes using only this many bits. Okay, so this is I've written this in this way, but you can also think of this as saying each time you use the channel, you send one physical bit. You can send C, big C, the channel capacity of logical bits through. Only in aggregate, you can't do it one by one, but when you're sending many, many messages, that's how many bits you can send. Okay? And that's saying that's both the best you can do, and there exist schemes that achieve that. And moreover, the channel coding theorem gives you a formula to calculate C. So how do you do that? So C is the maximum over distributions X of I, X, Y. So what do these things mean? So X is a probability distribution over channel inputs. Y is the probability distribution of channel outputs if you put in Y. Sorry, if you put in X. And this quantity I, X, Y is called the mutual information between X and Y. And it's equal to h of x plus h of y minus h of xy. OK? So what this channel coding theorem tells you is that if you have a communications channel and you know the type of noise it is, you have a very straightforward way. I mean, you have to do some optimization here, but it's over. This is a distribution over a single use of the channel. And so you just kind of vary over different possible distributions x, and you calculate this I of xy. And the best possible thing, that's the goal. That's the channel capacity for this channel. And so then this is from 1948 or something. So in the subsequent 70 years, people have worked a lot for different kinds of channels to come up with explicit codes that maybe have other good properties, like efficient encoding and decoding procedures, that get close to or achieve this channel capacity. So this is a theorem of great practical importance, as is the source coding theorem. OK, so let me end there for today. And tomorrow, I will tell you a bit about quantum channel capacity and the quantum analog of this, which is not quite as good. And then talk a bit about how you measure entanglement. OK? Are there questions? OK, then. See you tomorrow.